Hi, my name is Ron Lynch. I do web handling training and consulting, and this presentation is on Excel web tension modeling. Why do we build a model? Well, it helps you understand your process and your web path. It also points out what you don't know. But once built, the model helps you troubleshoot tension problems, optimize an existing web path, and helps you make material and equipment changes with confidence. This is just a preview of what I'm going to be talking about. A block. Each block represents a span and the roller that follows. So what is an Excel model? Well, these models are just basic web handling formulas arranged in convenient groups of cells that I call blocks. Each block represents a component, an idler, a nip, a turn bar, driven roller of some kind. Blocks are arranged according to the order of the components in the web path. And they do basic calculations for tension, strain, traction, etc. Blocks can be customized to represent specific roller types, a location or a function, or they can be anything else that you want. They can be user customized. What a model is not, at least this model, is it's not proprietary, it's not magic, there's no built-in logic. It does not make decisions for you. It does not fix itself or correct its own errors. It doesn't tell you what's wrong if it doesn't work. And it's not pretty. There's no bells and whistles. And so it is your basic calculator. Now, it's based on basic web handling formulas. Tension equals strain times material modulus times width, strain transport formula, idler drag formula, and the capstan formula. And these four formulas do most of the calculation in this model. Now, there are variations to the formulas, and I show these here so that when we talk about them, you know that they exist. Again, a preview. This is what the whole model is going to look like when it's done, so you'll know what's coming up. Now, this is based on a simple web path that we use in the seminar that I teach. We have a parent role, an idler, a dancer, or a load cell, an SRAP, another idler, sliding contact, two idlers, and in this first round, a nip at the end. So we've got 8 spans. The spans are numbered 1 through 8 as we start at the beginning towards the nip at the end, and each span is identified with the item that follows it. So span 1 is an idler span. Span 2 is an idler span, since a dancer or a load cell is just an idler. 3 is an SREP span, etc. So, again, another preview. This is the model of the web path that I just showed you, and we're going to go through this then in detail. Each block represents a span and the roller that follows it. The flow in the model is from left to right. Roller type describes the calculation. The name is user given, so you can give it and call it whatever you want. Design inputs, as I've done it, are in green. You can use any color you want. And for a driven roller, delta T is a calculated input. It's or a calculated value. It's an input for idlers only. Process inputs, I have boxed in green for tension and velocity in this case. Calculated results are in plain font. And EMQ is E to the mu theta without any formatting. I get lazy. So, first block in our model is the parent role block. And it's basically a place to enter things like modulus, width, the web name for this type of material, and any other data that you might want to pass from block to block in your model. You can put other things in here if you want to be able to do other calculations. The master roller in this model is a driven roller. It controls the velocity of the web, and it sets the flow rate for the web in this web path. Velocity and tension are inputs in this particular model, and that's because that's the way I set this example up. It's not always the case as an input. It may be set at a dancer or load cell previously. Flow rate is calculated in this block, and it's the rate at which relaxed web enters the web path and is fed down to other driven rollers in the web path. The velocity and strain in the master are the references that are used in the calculation of other blocks, and we'll talk about those. The master roller is the fourth block in the module. Now, normally I build the model just adding the blocks in a row, but I want to leap ahead to this one. In this case, the width and the modulus, which we entered in the parent roll block, are passed roller to roller down to the metering roll. And in this block, the CNF and wrap angle are required for slip calculations. The diameter is in here for reference only, as I didn't use it for anything. And the other inputs in this block are for tension and velocity. Now, in the master roller, the strain is calculated based on tension and the modulus and width, and then the flow rate is calculated based on the strain and the velocity. Now, if we look at the two idlers, the idler and the dancer load cell, we can see that the width and the modulus is just passed by reference from one cell to the next. And so that's how it finds its way down to the metering roll. Now, for these idlers, again, we need to enter the drag and the various properties that are shown here for the idlers. And the calculation that's done is we had a tension that was specified in the master roller. And so that tension minus the idler drag is equal to the tension in the span 2 in this case, and then span 2 tension minus the drag of the idler at the end of span 1 gives you span 1 tension. And so the formulas in here are simply chaining together tensions from the metering roll upstream, because that master roller, metering roller, is pulling the web off of the parent roll. Now, we're going to leap ahead to the next driven roller, which is the roller 8, the nip in this case. This is a fixed speed roller. It was given as one of the inputs for the model. And we're able to use the strain transport formula to calculate the strain, since we now have our references identified in our metering block. And use our tension and strain formula to calculate the tension. And we get a tension of 200 newtons down there. Now we're going to fill in the rest of the idlers and work our way back up towards the master roller. And so the idler calculation is the same. We have a tension in span 8. We subtract the drag of the idler at the end of span 7. That gives us span 7 tension. Subtract the drag from that, that gives it span 6 tension. We add our sliding component in here. Now this is based on Capstan formula, since it is sliding over this turn bar in this case. And so we can use our Capstan formula that the TL, the low tension on the upstream side, is equal to TH divided by E to the mu theta. And so we can enter that formula in the tension calculation for span 5. And then lastly, we can put our last idler in there at the end of span 4 and do the tension in span 5 minus the idler drag is equal to the tension in span 4. So we have completed this phase of the model. I do have spans 9 to 13. They're a copy of 4 to 8, and so I literally just copied and moved them down into position. And you just need to make sure that you get the right velocities in and double check that all the formulas refer to the right places. And so what the finished model looks like then is this. And so for the 13 spans that we have in this model, we have a tension and strain calculation for all of them. Now, we can also do a slip check, and that's in here if you have the COF and wrap angle entered. And what we find is that I've since changed the nip in span 8 to an SRAP here. And what we find is that SRAP is slipping. And so we've got a problem to solve. And that's one of the things you can do with this model. We can change coefficient of friction. We can change wrap angle. We can adjust T9, the downstream tension, or we can adjust T8, the upstream tension. And you can explore and decide which of these you like. Now, here's an example of a much more complicated model. Just to show you some of the other capabilities here, and we're not going to go through all of them in detail. So I have two zero-speed unwinds feeding two different webs. They go into slitters. Those slits are then recombined, and then those are recombined, so there's multiple combining operations in here, and a few processes to change the properties of the web along the way. So we'll show how those work. I start off, again, just a modeling technique, since we have two nearly identical unwind stands, A and B. I just modeled those the same. I used, they have a few idlers that are different, and so I used the same path for all of them. I just zeroed out the drag in a couple of idlers to represent the ones that are unused. And so it saved having to build the two unwind stands independently. So build it once, copy it, zero out a few things. Tension set point idler. Now this is one of the things you have to know to build a model, is where do you start? In this case, the large festoon is where they set the tension. And so now for idlers upstream of the set point, again, we use the subtracting the drag formula as we moved upstream from that 30 pounds to 29 to 28 to 27 to 26. For idlers after the set point, now you're adding tension to that 30 newtons. And another technique you can use here, since I didn't particularly care about the tension at each idler, is you can lump them together. Now I was using a drag of 1 pound per idler, I believe. And so 4 idlers is just 4 pound drag, and it's in here as a lump. Now, in this particular model then, the driven roller downstream of the accumulator was a variable speed roller. It was controlled by a load cell that was located downstream of it, and so the reference tension is actually set at this load cell, and the speed of the variable speed driven roller was found so that it would maintain that tension at that load cell. And so again, it's a manipulation of the strain transport formula to find the velocity if you know what tension you need to have. And so we have variable speed roller, and then it fed a load cell idler, which was the reference tension that was used everywhere in the web path. And that reference tension went over an idler, eventually did find its way down to the master roller in the web path. Okay, so downstream of the variable speed roller, we had a process idler number 1, which is modeled just like an idler after the accumulator set point. Process NIP number 1 in this case was an intermittent contact, and so intermittent contact, in this case it was very brief contact. It has no permanent effect on tension or strain or web velocity. So it's not really controlling the tension. So I just modeled it as a 0 delta T. Process rollers number 2 were, it was a non-contact process. So again, I just modeled them as 0 drag idlers, just as placeholders, so we could talk about them and describe them in the model. But again, as non-contact items, they have no effect on web tension or speed. And then idlers following process number 2 are just like, again, idlers after the accumulator. Some modeling tips here: think big, but start small. So I had the whole model in mind when I started, but I go through and build it up and understand it zone by zone. I've seen people build these monster models, and they start off and all the numbers are crazy and they don't know where to start. So I usually start as we did with the first model, with the first zone, get it working, understand what it's doing, and then move on to the second zone, get it working, understand what it's doing. Troubleshoot and solve problems zone by zone. It's the easiest way to do it. The other thing I do is start with inputs that are intuitive, so that the results are easy to interpret. Round numbers for idler drags and for set point tensions and for velocities, so that intuitively, if you've got a 1 Newton drag at an idler, it's easy to add together what the tension should be and understand that your model is calculating correctly or not. And so I found that to be useful. Be careful and consistent with units. You find that units sometimes are in U.S. customary units in some specs, and SI units and machine set points, and so you've got to either go all one way or the other, or make sure that your formulas account for the differences and that you understand what they're doing. And then if you do named references and things like that, and they're cutting, copying, and pasting blocks around in the model, or inserting and deleting rows, make sure your references don't get lost and that they're in fact pointing to where you think they should. So now what do you do with the model? You've built it. First off, does it match real life? Does it predicting what you think you see out there? If it's perfect, that would be amazing, because that rarely happens. If it's close, that's good. You see tension sort of go in the orientations that you think they should go, up and down as you think they should. If it doesn't match real life, you've got to ask yourself, what is it I don't know about my process? The model may not be right, but it's not right because there's something you didn't understand, or the machine is not the way you thought it was. And it's something to troubleshoot. If your model says it should run perfect and your line doesn't run at all, you need to sort that out and understand what is the discrepancy. It might be the machine, it might be the model. Now, the other thing you can do with this is you can go back, and if you do want to get a little bit more complex in your models, you can plot your tensions, you can look for high and low tensions, you can compare them to your tension criteria for high and low tension, high and low strain. And so you can plot things out and see, what are your peak tensions? Where are your big tension drops over rollers? Could those be problem areas for wrinkles or slipping? And you can do experiments. Now, this is where you might say, okay, this is running my normal raw material, but I want to run something lower modulus. Is it going to run? What are my tensions going to be? Are there speeds of rollers that I might adjust? And do it in the model before you get out on a converting line and have to try and make it run when you're using raw materials and consuming production time. And so you can do your experiments on the model, you can do your what-if questions, you can do your troubleshooting, you can do equipment modeling changes, and experiment with it. Learn what happens if I change this roller, and do some questions. I helped a customer build a model once, and we came to a roller, and nobody could explain what it did. It was a driven roller, and it turned out it was not needed. It was left over from some previous iteration of the machine, and in fact, it was creating problems for them. But nobody really understood why it was there, and they just left it there. But the model identified that the roller really didn't need to be there, so they went out, took it out. Line actually ran better with it gone. And so you can do what ifs, you can ask questions, you can. I've typically found that by the time you get done building the model, you know more about your machine than you did beforehand, and it's always good. Are there any questions? And I hope to be in person. Maybe I'll be online. We'll have to see how things go. But questions one way or the other. Thank you. You've got emails at the beginning and end of this. I am sometimes webhandlingmaster@outlook.com. Thank you.